All right, so thanks everyone for joining and let's get it started. Today we're going to talk about detecting silent machine learning failure in models in production. And it's going to be kind of an introduction to how you should do machine learning monitoring. I'm Wojtek Kuberski. I'm one of the founders of NaniML. We are a fully open source Python package for detecting silent model failure and, generally speaking, monitoring your machine learning applications from the data science and business perspective after they have been deployed to production. So today on the agenda, we have really three things. First, we're going to talk about two main reasons why machine learning models can fail silently in production, which is the data drift and the concept drift. We'll define them and we'll talk how they can impact performance and how they can cause model failure. Then we're going to talk about performance estimation, starting with why you need to estimate the performance of your models, even if you do not have access to target data. And we're going to talk about why you rarely have access to target data. And then we're going to actually discuss the algorithm about performance estimation. And we're going to delve slightly deeper into the technicalities of it, when it's possible to estimate performance and when it's not. And then we're going to wrap up coming back again to data and concept drift. And this time we're going to talk about detecting it in order to kind of troubleshoot the issues and try to figure out what is the underlying cause of performance issues and potential model failure. But before we get started, I want to quickly kind of give you an example use case for which model monitoring would be absolutely essential. And this use case is going to be the loan default prediction. So what we have is we start with some credit scores, we start with consumer information, and we're trying to predict whether a given consumer or customer is going to default on a loan. So it's a typical banking use case, and we're going to define a target here as a non-payment within 1 year. So we will have to wait entire year after making the prediction to see whether this prediction was correct or not. So we're going to be working with a lot of uncertainty once we deploy the model to production, and also lots of potential, both positive and negative impact of the use case, because if we misprice the loans or we misjudge the risk of customers not paying back the loans in a systematic manner, we might expose the entire business to huge risk. And of course, we need a technical metric to, in a way, evaluate the quality of the model. And for that, we're going to use very typical ROC AUC metric for binary classification. So let's get started with talking about potential causes of machine learning failure. So starting with a quick refresher, what are we trying to actually do when we train a model? So we have a true pattern that exists in reality, not necessarily fully in the data, but there exists a pattern. And this is the pattern that we're trying to capture. This can be a very simple pattern. It's very easy to identify. For example, the pattern might be that people who don't have any income will always default. That's a very simple pattern that would be very easy to learn. However, most patterns that we're trying to learn are so complex that it's impossible to just write it out. And that's why we need deep neural networks with millions and millions of parameters. So we have this true pattern. Then we're going to sample some data by collecting the data. Maybe this is going to be the data of our all existing customers, but not all customers that we're going to have. So we still don't have the entire population available. So we're going to sample this data from the population. And then what we end up is we're going to end up with our training plus validation plus testing set, when we're going to have some kind of, let's say, class balance using our example with binary classification. And we're going to have a number of features that hopefully relate in some way to the target that we're trying to learn. So that's kind of the setup. And now let's see how the setup will be affected if we have data drift. So in case of the data drift, we get this something and this something changes. So the true pattern that relates, for example, how people behave to how likely they are to default on a loan will not change. We have exactly the same pattern that we're trying to learn, the pattern that we had in the training data set, and in production is going to be exactly the same, but the customers themselves will be different. Maybe they will be younger, maybe they will be richer, maybe they will be poorer, maybe the gender balance is going to be different. There's going to be some change in the distribution of the model inputs. And it's a joint distribution, so maybe on univariate level, all the distributions will look very similar, but the correlation between, let's say, age and income will change significantly. That means that our data itself will look differently maybe the pattern that would have been later is different, but the underlying pattern is still the same. So we can define it a bit more formally as a change in joint model input distribution. So basically how the data set looks like from distribution perspective of what we have to work with. And we see here that taking one simple example with just one input feature and the frequency of that data point, we'll see, for example, that maybe it shifted upwards and that just data drift. Now we're going to talk about concept drift, the second main reason why models can fail in production. So here we see the change in the true pattern that we're trying to capture. And under pure concept drift, if there's no data drift, we will not see the change in the sampling mechanism. So the actual data will look more or less the same, but the underlying pattern between what data we have and the target we're trying to predict is going to change. Maybe in the past, it was almost certain that people who have high income are not going to default on a loan. That's a reasonable assumption. But now, because something has changed, maybe the times are more uncertain, these people are not so certain to pay back their loans. So we have a change in the pattern that relates the model inputs to the target. And whereas concept drift may or may not lead to model failure, I will delve deeper into when it might happen and when not. Concept drift almost always leads to model failure because the pattern that we learn is no longer relevant. And if we get data points for which this pattern has significantly changed, the model is very likely to make a wrong prediction. We can also visualize concept drift in a slightly different way when we look at the class boundary instead of full distribution, and we'll see that the distribution of the data points is going to stay roughly the same, but the class boundary might change significantly between the training data and the production data. And again, just to define it a bit more fully, the concept drift is the change in the underlying concept of pattern between the target and the model input. So it's a probability of the target of the Y given the data. So that's basically two main reasons. And now let's take a step back and discuss why we need to monitor performance and not just look at concept drift and data drift. So why performance matters? So first of all, as I already mentioned briefly, data drift does not always need to drop in performance. If the data moves from one region in the input space where the model is performing very well to another region where the model is performing equally well, we do not expect to see a drop in performance. Even we might see a slight improvement in the model performance, maybe if the data moves from being very close to the class boundary to being slightly farther away from the class boundary. So then for the model, it's easier to differentiate positive from negative examples, again, using our ongoing example with loan defaults. Another thing is just simply, this is something that we've been optimizing for in training, whether we're evaluating our model using accuracy, RMSE, F1, any other metric. This is the metric that we are just optimizing for explicitly when training and picking the model that has the highest, normally the highest metric. So we should continue to do so, and we should continue to care for it after we deploy the model. And the most important, also most obvious reason is that technical performance, so technical metrics are just a proxy for business impact. And business impact is something that matters in the end, nothing else really matters. So we need to focus on performance. And now let's talk about how we could focus on performance. So first thing is just measuring the performance. Let's say that we work in high frequency trading. In that case, we could make a prediction and see whether the prediction was correct or not, literally milliseconds after making the prediction, because we'll see whether the price of an underlying asset will go up or down. However, in most of the use cases, we do not have access to ground truth right after making the prediction. So using, again, our example with credit loan default, we experience delayed data here, delayed target data, because we need to wait an entire year before we can simply calculate performance, before the targets are simply not there, they are not available, they have not been realized yet. Another thing is, even if we do get the targets or the labels, they are quite often incomplete. In our ongoing example, we do always get the labels about the people we decide to give loans to, but we never get the labels for the people that we decided to not give the loans to, simply because we don't know whether they would have paid back the loans or not because they haven't received them in the first place. So even then, we do not have access to full labels as we would like to. And then the last reason why we rarely have access to ground truth is a full family of use cases, of automation use cases, when we are trying to replace a human doing some task. It's normally a menial task like document classification, text summarization, maybe some form of image recognition. There, the whole idea of the use case is to replace human with a machine. And then, of course, we can do spot checking. We can maybe have humans double check the machine learning system for 1% of all data. And for those, we will get the targets, the labels. But for the remainder, the vast majority of the data points, we will never get the ground truth. So in summary, we generally do not have the ground truth, and operating a model in production without being able to measure its performance is something that's inherently risky, and we need to do everything we can to de-risk it. So now let's move on to this de-risking. So let's talk about how we can measure or estimate the performance without having the ground truth. And I'm going to describe very briefly in high level an algorithm that we developed at ManyML that is able to do just that. So imagine that we have our binary classification model, and we have here in the picture on the left, we have two classes, and we see that the model is very confident if the predictions are close to kind of the center of first class on the left or the second class a bit on the right. So it looks a bit like a butterfly. And if we're in the green regions, the model is very certain of its predictions. We would also expect the model to perform very well in these regions because it's just a simple task to classify a data point in that region. And our data is distributed in a way you see with the blue dots here. So there's few data points that are close to the class boundary, but mostly the points are in the wings of the butterfly. So it's quite easy to really determine whether somebody's going to pay back the loan or not. And now in time, because maybe economic circumstances change, we will see way more data points that are close to the class boundary. So you don't really know whether these people are likely to pay back the loans or not. Then we would expect the model to be less confident. And this expectation of, less confident, and also the model to be less performant if there's more points for which the model is less confident. So basically, assuming that we can trust the model to evaluate its confidence well, and that's a huge assumption, we can then link this confidence to the performance. If the model thinks that it's not going to perform well, it's very likely that it actually does not perform well. And this is something that we can do very easily with probability calibration. It's an established technique to make sure that if the model says that the model score is 0.4, let's say, that it actually means that there is a 40% chance that this given point is going to belong to class 1. And if we make sure that these probabilities are calibrated, we can then transform this probability into the expected error. And more specifically, expecting chance that this given point is going to be true positive, false positive, true negative, or false negative, depending, of course, on the threshold that we're going to impose and this probability. Then we end up with this expected mini confusion matrix. And if we just aggregate enough of these points, this expectation is going to be closer and closer and closer to realized performance that we don't know yet, but we know it's going to be getting closer to that. So if we then chunk our data in production into reasonably sized chunk, we can, with certain confidence bands, estimate what is the performance of the model without, again, having access to ground truth data. And that algorithm fully covers the impact of data drift on performance. So if data moves from one region of high certainty to another region of equally high certainty, we will see that the expected performance has not changed. If it moves from uncertain region to another uncertain region, the same thing. If it moves from a certain region to an uncertain region, we do expect to see a significant drop in performance. However, of course, we have two assumptions here. First assumption is that these probabilities are well calibrated. And this is something that in our library we do behind the scenes, and it's also a good practice just to always give calibrated probabilities to the business stakeholders who will then act on it, or to downstream services that will use the data that the model outputs, so that the risk is properly handled or priced in, and the downstream services can use not only the class information, but also the certainty information. So that's the first assumption. The second assumption is that the underlying pattern between the model inputs and the target, and also the probability that these data point belongs to a target, does not change, which means that we are assuming here very strongly there's no concept drift. So using this algorithm, we can kind of solve the problem in 50%. We can exactly narrow down and pinpoint what is the impact of data drift, but we cannot say anything about the impact of concept drift on performance and whether the concept drift is even here. And now let's look how this thing actually looks in reality, whether this algorithm works reasonably well. So here, for the purposes of this presentation, we run a quick experiment on a California housing data set, which is something that I think most data scientists are familiar with, because back in the day when you were still studying, or if you're studying now, this is something that you probably used to create some easy toy models. So we trained a very simple model on the California house prices data set, which is available in scikit-learn and a million different other places. We thresholded it to turn it into binary classification, just to have a very simple metric here. And you can see that the log AUC of our model and the estimated log AUC that we estimated using this algorithm without using any labels after we have deployed the model, so after this line. And we see that one and the other is reasonably close to each other, so we can, with certain, of course, uncertainty, estimate the performance of the model. And we could see, for example, that in this region here, we would be worried that something is going wrong, and there is significant data drift in regions where the model is not certain of its predictions. So we should probably take some action to fix that, or maybe stop the model from operating on these kinds of data points. Now we finished the second section, which is the performance estimation, and we're moving into the third section, which is, okay, the model has failed. Now what? How do we fix it? What can we do to really fix the issue and make sure that the impact is again there and we're not losing money anymore? So then we need to go into kind of a root cause analysis when we look at the data drift and see what are the things that have changed in the data that might be the potential cause, and what can we do about it. And we can do it in two ways. First one is just looking at it feature by feature. So we're going to do univariate, because we're looking at a single variable. We're going to do univariate data drift detection, and we can do it using very simple statistical tests that just compare two distributions. The distribution of a reference data, for example, our test data, for which we know that the performance is satisfactory, and the current data when we know that there's some issues with performance. And we can do it feature by feature, and we'll be able to see which of the features has significantly changed. But that has a couple of shortcomings. The first one being, if our model has thousands of features or even hundreds of features, we will see data drift all the time and basically everywhere. Because using statistical tests, we expect a certain number of false positives, and if we run enough tests, we're basically guaranteed to see these false positives, and we're gonna drown in alerts. We're gonna get so many alerts that they will become completely useless. And the second shortcoming of the univariate method is that if there are more complex or subtle changes in the data, maybe the correlation between two features has changed, but the features themselves look on the distribution level reasonably similar, then we'll not be able to detect it with the simple univariate tests. So for this reason, we will have to use a bit more advanced multivariate data detection techniques. And here I'm gonna quickly go over one idea that has been used in both our library and I think 2 or 3 other papers that have been written quite recently. So what we're going to do is we're going to try to measure how the structure, the geometric structure of the data has changed in time. And to do that, we're gonna learn the structure, and we're gonna then measure how we can reduce the dimensionality, compress the data using this assumption about the structure, and then decompress the data. And if the structure is still the same, then this compression, decompression should be reasonably lossless, or the loss should be low. But if the structure has changed significantly, then we expect to see that this compression and decompression is going to become more and more lossy. So to be specific here, we're gonna do some kind of dimensionality reduction when we compress the data set, and then we're gonna do the inverse transform. We're gonna learn or fit this dimensionality reduction, such as PCA, UMAP, or variation autoencoder on our reference data, for which we know that this is the kind of distribution that we desire. And then we're going to reduce dimensionality and inverse transform the analysis data. So that's what you see here. We take the original data, the original analysis data, we project it to a latent space, so the reduced dimensional space, and then we're going to reconstruct it back. And then we're going to compare the original data with the reconstructed data. And if we see that there is a significant difference there, which we can just measure, we're going to know that there is some form of complex data drift that's going on. And then we can start digging deeper and figure out what kind of drift there is actually happening. So now let's talk a bit more about this data reconstruction algorithm and what are really the requirements for this compression algorithm to be relevant here. So first of all, this encoding or this compression needs to learn the internal structure of the data. This is the basic premise here. Then second, the encoding needs to reduce the dimensionality. We need to actually compress it in order to force some losses if the compression and the structure is not correct. And then we need to be able to inverse transform this compression so that we can measure the potential loss. And there's last kind of small requirement is that the latent structure, so the compressed dimensionality, needs to map in a stable way to the original space so that the measurement of the loss is meaningful. If we just train, let's say, an autoencoder that is not variational, very small change in the latent space can result in huge change in the original space. So we'll get insanely high error very easily if we just slightly change the data. So then we're gonna do this transformation and then inverse transformation, and we can measure the reconstruction error. So we will simply measure the dislocation of points before and after the reconstruction. And then we'll just measure it using any distance metric, any metric. We're using the mean Euclidean distance, so the simplest one you can think of. And then we're going to get a reconstruction error. And this reconstruction error is one number that measures basically the totality of data drift within the data, which is kind of a very nice way of seeing how stable is your data set. And can, for example, replace simpler measures that are less accurate, such as population stability index. And we will see that this reconstruction error will not start at 0 because the compression is supposed to be lossy. And we will also see that if it goes up, then we have data drift. If it goes down, we also have data drift, quite interestingly, because it means that the internal structure of the data has changed in a way that right now this learned structure is actually closer to the real structure. So we see a smaller loss here. And that's basically it when it comes to the data, data drift. I'm just going to give you a very quick example here of a data set, a very simple toy data set, for which univariate data drift will not work, but this proposed method will work quite well. And what you will see here is we see one reference data set, which is the blue one, and another orange data set, and we see that on the univariate distributions, they are basically the same. They're just rotated 90 degrees. But because they're rotated 90 degrees, it means that for each, the x-axis and the y-axis, there's no change in distribution. But of course, these distributions are completely different in the multivariate setting. And we see that our method using PCA as the compression and decompression algorithm can pick it up reasonably easily and actually alerts us that something has changed significantly. So let's summarize. So first and foremost, data drift and concept drift are the leading factors of model failure. And while concept drift does almost always lead to drop in performance, data drift doesn't. So just monitoring data drift is not enough to really have any reasonable indication of what's going on in when it comes to your performance. Also, production targets are often not available to calculate performance. So instead of calculating performance, we have to estimate it in some way. And for that, we have this algorithm that takes into account all kinds of data drift and its impact on performance, and then just outputs a number. And this is really the key to monitoring, because if you do anything else, it doesn't really give you reliable information about the most important thing, which is what is the business impact and what is your technical KPI. And that's it. So thanks for listening. And if you'd like to learn more about that, either visit our website, send me an email, or preferably a LinkedIn message, or check our GitHub. We are right now in open beta, so you can just go to our GitHub. We released it 2 weeks ago, and you can see what's there. You can give it a try, just click install it and run it on your data. Visit the documentation, visit our blog when we talk more about how to really do machine learning monitoring, how to do AI observability, and how to detect silent machine learning failures. And that's it. So thank you very much. And now let's have a round or two of questions. Yeah, so I have a question about code example. So I will share the GitHub link, and I'm going to give you the GitHub link here in the chat as well for ease of access. So here's the link. Oh, yeah. Yeah, so I have a question, is that whether the reconstruction technique actually tells us whether the population data is unstable or not. So it tells us whether the data has happened or not. It doesn't go as far as telling us whether there's some kind of inherent instability in the population, because this is something we cannot really know upfront. It's very hard to know something upfront about the population. We only ever get access to the samples. But it does tell us whether the samples that we had access to change significantly in time or not. When it comes to solving it, that is a very hard question, and it's going to be very strongly use case dependent. If we see that there is, again, strong data drift and we see unstable population, but our models generalize well, so our performance estimation still gives a straight line, everything's good, there is no reason to be worried. If we see that there is a drop in performance, then the first step should always be to just retrain your model on entire data and redeploy it, not even redeploy, just rerun it on historical data on the parts that you did not train on, and see what's the performance there. If you don't have access to the performance, some data, you could also use performance estimation to evaluate the new model and do some kind of A/B testing there. And if that solves the problem, you're great. If it doesn't solve the problem, then unfortunately, a human in the loop is needed, where you as a data scientist need to come back and see whether there was some kind of structural change in the data, whether there was strong concept drift, and whether you need to maybe only use the new data to develop a model, or do some kind of covariate shift on all data to make it more similar to the new data, et cetera, et cetera. So then coming back basically to model development again. Happy to help. Yeah, so I got another actually great question, which is how often do you recommend monitoring / reviewing the data for data or concept drift? And this is assuming a small team that is often stretched and either building models or reviewing models. So that is something I would recommend doing, again, based unfortunately on the use case. So there's two things here. One is you need to look at how often you expect it to change from kind of the business perspective. And if you're doing sales of products that are seasonal, you will definitely see strong data drift from season to season. So that's something you should definitely do there. If you do recommender engines, then customer preferences can change really daily. So then you should really do it daily. So you should basically, you know your data, you know the cadence and the dynamics of your system. So you should do it according to that. Plus, you also need to have enough data to really know whether this change is significant and persistent versus something that's just noise. And that is something that we do provide in our library when we automatically chunk the data and chunks that are big enough that if we provide some kind of performance estimate, this performance is reliable. Because if you do it in streaming manner and you only get one new data point every time we reevaluate, you will really not get much because this one data point, each single data point is just noise. But once you get enough of them, you will start to see patterns. So rule of thumb is that you need to have between 1 and 10,000 data points to really tell you that there is a significant change in performance. That I think should answer the question. And good thing is that because you can just use a software, this review should not take long. What I would recommend is that you put it, you take some code from NanoML, you put it in Airflow, you run it, let's say weekly, and then you just look at the results. If the results of performance estimation are good, if there's no alerts on the data reconstruction used for detecting multivariate data drift, if you don't see the errors in these two things, don't even look at univariate data drift because you will for sure see a lot of things there, but it's mostly going to be false positives. And only start really caring about stuff if you see either drop in performance or significant multivariate data drift. Then I have the next question, which is, have I read first order motion model? I unfortunately have not, so I am not qualified to answer the question whether it can reduce the computational power to learn. But Andres, if you want to elaborate in a comment, go ahead and I will do my best to help. Okay, and I got a link. Let's take a quick look. Okay, this is framework for image animation, and I am unfortunately not qualified to say anything there because we're right now mostly dealing with tabular data. So I wish I could help you, but it's not this time. So feel free to just send a message in the comments in the chat. I'm happy to answer, and if not, we're gonna be wrapping up in around 3 minutes. Also, again, happy to hear any issues you might have had in your models. If you're already curious to see if you already experienced some kind of model failure and what was the business impact of it. Yeah, I see a few comments. Thanks for answering the question. So I'm happy I'm useful. Oh, I'm getting a lot of comments now. That's great. So I have another question, which is, what site or book do I personally like reading? That's a very good question. I do like OpenML and everything they write about. I second everyone else's recommendation of reading the Bishop book on the pattern recognition. I think that provides very nice framework about how to do machine learning from more like Bayesian approach. And I'm generally a huge fan of Bayesian approaches to machine learning just because they're so elegant and they really give you the complete view and they explicitly state all the assumptions. You, of course, always have a prior. If you create a random forest model, you have a very strong prior there about how the data can be structured, but this prior is not very explicit. So you might violate some of the assumptions without even realizing that. If you have a logistic regression, you have so many different assumptions. Some of them are infinitely strong prior, so if you validate them, it's just not going to get modeled. Some of them are not. But again, they're not very explicit. If you work with Bayesian learning, you just need to specify your prior distribution. And I think that just gives a very nice understanding of what's going on, what are the assumptions that you put in the model, and what comes out of it. So there's that. And now another question is about concept drift. Yeah, so the question is, are data drift and concept drift often confused as a cause for degraded machine learning performance? And I would say definitely yes, and not only they are confused as a cause, but they're also confused with each other. If you read any papers, especially older papers about data drift and concept drift, data drift is sometimes also used to mean concept drift as well as data drift. And we decided to just settle on data drift, meaning model input, change in joint model input distribution, because this is something that the most kind of cited papers used, and concept drift as change in the target given the data. But even in scientific literature, you will see these two confused. And there's another very interesting reason why you could confuse these two is that model data drift and concept drift happen at the same time very often, because you could actually look at concept drift as data drift in unseen variables. If you had access to all the variables in the world, all the knowledge in the world that exists, and you knew everything, you would be able to model everything up to, down to quantum level, extreme quantum level, which is truly random. So all the stuff that you really cannot model, it means that it's not in the data, but these variables are there, they are hidden variables. And if these hidden variables change, then you also see the change in the target, which you cannot model, you don't see it, so that is concept drift. But as these change, it's also very likely that some of the observed variables change, because maybe there's underlying reason why these two change, and maybe they will change at the same time. So then you will see drop in performance that is partially due to data drift, but also partially due to concept drift. And there is a silver lining here, is that first and foremost, right now, the algorithm that we're using can detect drop in performance due to joint concept drift and data drift, because it will take the data drift part fully into account. But it will most likely underestimate the impact of this drift on performance. So it will tell you the performance is dropped, but in reality, the performance will have dropped significantly stronger. But at least you will see that there is a quantitative change in performance, even if you cannot be really precise about the magnitude of this drop. And another reason to be quite optimistic here is that if there was pure concept drift and nothing really changes in the data, we cannot detect it. It just happens and we're basically doomed. There is no way to figure that out. This is silent failure that cannot be checked. However, because concept drift and data drift happen at the same time quite often, we could try to estimate concept drift from the data drift. So I hope that answers your question, Pierre. And now moving on. I have a question about any approach to track drift for text data, so for NLP use cases. And I would say yes, and why I would not recommend using univariate approach there, because tracking individual vectors doesn't really make sense. What I can say is look at the vectorized data. So after you do your Word2Vec or Word2Vec 2.0, look at this and do the data reconstruction on it. You can just treat it as tabular data. If you see that the vectors change significantly, the embeddings change significantly, you know that there's data drift. You will not be able to track exactly which word frequencies change and things like that, but this is something that it's not very useful for you anyway. I would say that in NLP, the data drift is more of a yes/no thing than trying to figure out what exactly changed. So then you can just use the multivariate data drift, the data reconstruction approach that I described. And it basically should work out of the box as long as you work with the embeddings and not the text data. All right, so I see no more questions, and we are just 5:45 to 6, at least my time, local time in Lisbon, by the way. So thanks a lot, everyone, and I'm going to give you one last minute if you want to ask any questions, and if not, do shoot me a message on LinkedIn. I'm quite active there, or also I invite you to join our Slack community, and you can find the link to the Slack community also on our GitHub page. So just click join Slack there, and you'll be able to do it, and we will answer within minutes. And I already see Arab is linking to my LinkedIn, and hopefully he will link again to the GitHub in a second. If not, I'm gonna do it. Yeah, so here's the link to GitHub again, and just go there and click join Slack community. And we are happy to answer any of the questions. If you have more engineering questions, as you could probably already guess, I'm not a very good engineer, but we have an amazing engineer on board, and he will gladly answer any questions about the integration and how to get Action Learning deployed and monitoring your models in production. So that's it. Thanks a lot, and yeah, hope to see you here or there. Oh, I actually got 2 more questions in Q&A, which I did not notice, so I'm going to answer them before we wrap up. They are, one of them we already got, so I'm just going to skip it. And the second one is, how should we debug ML models? That is a very hard question. And long story short is, start with looking at the performance. If performance is fine, you can continue. If the performance, ideally computed performance, if not, you can go with the estimated performance, which is sometimes equally good. And if you see drop in performance, then you need to start debugging. First, look at the univariate data, look at whether there are some features that have changed that you know are important, or you know that even they're not very important from a feature importance level. Business for some reason cares about them. Maybe they're important in a way that was not captured by the model. And then you can also look at general data drift to see if there's any more complex issues. And then, unfortunately, you need to basically go back to developing the model again and try to craft new features. Crafting new features might be able to solve the issues if simply retraining doesn't solve it. The first step should always just be retrain the model on new data if you have the ground truth, and see if the performance improves or not. All right, so thanks everyone, and till next time.